didn't get all of the elementary optical transform matrices last time. We have one remaining, and that's the reflection optical transform matrix for reflection from a spherical mirror. So let's take a look at that. And we have our sort of usual concave spherical mirror. I didn't write it on here, but it's the usual radius r. We have a sign convention with it, so just remember that. I have the center of the spherical mirror, and if I draw a ray here, this is the incident ray, and then there's the reflected ray. Uh, the uh, the optics it can be gleaned primarily from the law of reflection, and that the angle of incidence, that's alpha 1, has got to be equal to the angle of refraction. And remember, this radius here is a normal to the surface of that spherical reflecting surface. So I know that alpha 1 has to be equal to alpha 2. We just need to translate that into uh, the uh, uh, the uh, uh, the thetas and the y variables for this particular set of rays for the entry and the exit. And here's the entry ray. If you look at that, it again we're looking at paraxial rays, so this distance y1 is effectively the same as this arc length here, and the the angle theta 1 is the same as this angle over here, and so we could write a couple of things with that. And then likewise with it exiting over here, well, its height y2 is this ray, and it makes the angle theta 2 with respect to the optical axis. So we'll look at that and try to get a transformation between y1 theta 1 and y2 theta 2. First thing, let's get a couple of simple relations. Let's look at theta 2 here. And if you look at this is alpha 2, that's the angle of reflection. And this angle phi is the angle that the radius makes to where it hits the mirror. And by alternating angles, parallel lines, well, this angle up here is also phi. And you can see from that alpha 2 has got to be equal to theta 2 plus phi. And so theta 2 is alpha 2 minus phi. And at least to a good approximation, well, for phi, this is really exactly right, I suppose. This arc length is r times phi if I express phi in radians, so the arc length here to the point where it hits. But that's very, very nearly y1. And so the arc length really should be s divided by the radius here should be equal to the angle phi in radians. Now we have to remember our sign convention, and our sign convention is that for the concave mirror, that's a negative r. So if I honor that, this r here is negative, and so I have to take a minus of it to get all of this to be a positive value. And so I substitute for phi here this y1 over minus r, and it's subtracted. I can do a similar thing for the alpha 2. Again, if you look at that, or alpha 1, I should say, alpha 1 is the angle of incidence, and it's related to, I guess if you if I look at, let's see, which triangle do I want? I want to look at this triangle here, from here to here, want to look at this little triangle here. Phi plus alpha 1, so phi plus alpha 1 plus this angle, but this is a straight line, so this angle is 180 degrees minus theta 1. Here's angle theta 1. This is a straight line, so this angle at this corner, so I've got a triangle, and the sum of phi plus alpha 1 plus 180 minus theta 1 has to add up to be 180. And that gets me a relationship between theta 1, which is just alpha 1 plus phi rearranging. And then, of course, phi, again, is this y1 over minus r approximately. Again, we're looking at paraxial rays, where this arc length is very, very nearly y1 and y2. So we have this. I solved this one for alpha. Theta is equal to minus y1 over minus r. And now then I know the angle of incidence, alpha 1, is the incident ray, and alpha 2, the angle of reflection are equal. And so I can write alpha 2 as this alpha 1 is equal to alpha 2, and so I can simply replace the alpha 1 up here with alpha 2, and that gives me this relationship. Then I can use that to plug in for alpha 2 up here. And so alpha 2 minus y1 minus r is going to be theta 1 minus y1 over minus r minus y1. I've got two minus and minuses, so I might as well make that a plus. And I've got two of those, so I get ultimately theta 2 is theta 1 plus 2 y1 over r. And I'll reformulate that again as just theta 1 plus y1 over r over 2. Mainly because I know that the focal length of a spherical mirror from our previous studies of it is just the radius divided by 2. And remember, there's a sign convention associated with that. R is positive, a positive number if it's a convex mirror. And in this one, the case up here, it's actually a negative one. The case that I've drawn is for a concave mirror, it's less than 0, so it's negative. And that gives me all I really need. I know that the entry is at y1 and the exit at this point here, the exit is at y2, so that gives me that y1 and y2 are equal, or y2 is equal to y1. And then this relation, I can go ahead and use the fact that f is r over 2. I'll rearrange it. This one becomes y1 over f, the focal length of the mirror, plus theta 1. Once you have that, then you can read off the matrix of coefficients to get the transfer matrix. Y2, the column vector y2 theta 2 is the matrix of coefficients, and times the column vector y1 theta 1. So reflection, again, this is I'll go ahead and use r for reflection of a mirror is 1 over is 1 0 1 over f 0, and then f is r over 2, so some people like to write this as 2 over r. But remember, there's a sign convention. R is positive for convex mirrors, and r is negative for concave mirrors.